Hello, everybody, and welcome to my presentation for DDL 2021. My name is Andrew, and I'm a student down at Monash University who's just about to finish his PhD, working within the inhaled oxytocin team under the guidance of Professor Michelle McIntosh. And so this piece of work that I'm talking to you about today is all about how we optimized our spray drying yield and production efficiency in order to move towards a more affordable spray dry product for global health applications. And so the global health application that we're actually targeting is reducing the burden of maternal mortality. And we know that the burden of maternal mortality is incredibly disproportionate. There are several orders of magnitude more deaths per 100,000 live births in countries in sub-Saharan Africa than there might be in countries like the UK. And we also know that about 20% of those deaths are actually due to what's called postpartum hemorrhage. Postpartum hemorrhage is a loss of 500 mils or more of blood up to 24 hours after birth. And so the reason that this incidence of PPH is so inequitable because PPH is entirely treatable and preventable, namely with 10 international units of oxytocin delivered via intravenous or intramuscular administration. Now we know that oxytocin costs around 33 US cents per dose, so it's a relatively cheap pharmaceutical for these countries to be procuring. There are, however, a number of barriers to effective treatment with oxytocin, namely that it requires refrigeration between 2 to 8 degrees for its stability. And so it needs to be kept in the fridge throughout the life of the product. And also there is a substantial number of countries in sub-Saharan Africa that are using poor quality oxytocin as a result of these barriers. And so the Inhaled Oxytocin project is all about developing a dry powder formulation alternative that uses a spray-dried trehalose formulation to impart a level of heat stability in order to address some of those barriers that I just mentioned. And the idea is that it's going to be simple to administer using a DPI, and so you won't need necessarily trained healthcare staff and midwives to administer it. Now, the Inhaled Oxytocin project has been going for a number of years, and the product has some proven technical attributes in clinical studies. It has a level of clinical success. The problem that we're running into is that we're not actually sure if we can manufacture it at the affordable level that we need to in order to obtain a sustainable level of uptake of the product in these low-income countries. And so how are we going to address this? Well, namely by improving the sustainability of our primary powder production method, and that is spray drying. And so there are a number of affordability challenges that I just mentioned, namely that it has to be viable in the long term. Sustainability in this context means we can sustainably manufacture it at a cost that's appropriate for low-income countries. In addition to that, the main cost for spray drying for us is actually the time spent using a commercial spray drying facility. Also, the increased cost of material that you would see when you use spray dryers that actually produce a low yield. And so the yield of production efficiency or yield per unit time of a spray dryer is actually really dependent on the level of powder adhesion to the inner walls of the spray dryer, but also the collection efficiency of the cyclone. And so many pieces of spray drying literature actually use what's called a Bookie 290, which is a smaller benchtop system. We're going to be using a pilot scale spray dryer called the Procept, which is a more physically representative spray dry of what you would see at a commercial scale. It can dry the powder to a greater extent, and it has a slightly better collection efficiency depending on what kind of powder you're making. Now we want to improve the yield of an already existing product. And so that means we need to maintain the tightly engineered powder characteristics of the inhaled oxytocin particle, namely the amorphous solid state, the particle size within the respirable range, the small D50, the low moisture content, and the high TG, which is going to be speaking to the stability of the product. And so namely, we want to use a design of experiments approach to actually improve yield while maintaining all of those desirable characteristics. And the methodology that we chose was a 2,4-CCD or a 2-level 4-factor central composite design. The spray drying processing parameters that we were going to be adjusting in this study were the liquid feed rate, the concentration of the feed solution, the atomizing gas feed rate, and the inlet air temperature. We were going to be producing around 30 powder batches for this study, and then doing a whole bunch of physical characterization techniques on those powder batches. Then we were going to construct a model and ideally optimize it for yield and production efficiency. And then we're going to try and validate that model as well. And so let's talk about some key findings. Now, I'm going to be referring mainly to a couple of the key processing parameters, but we did actually map everything, which allowed us to actually create the model accurately in the end. And if you would like some more information about what we did here, then please don't hesitate to reach out to me. And so with that in mind, improvements to yield were largely a result of increasing the liquid feed rate and the concentration. Now, the liquid feed rate is just the fluid entering the spray dryer per unit time, and the production efficiency is the yield per unit time. So increasing the liquid feed rate was obvious we were going to see an increase in the production efficiency as well, but it was also good to see that concentration also resulted in an improvement in that response. So increasing the liquid feed rate and the concentration generally increased the yield and production efficiency, but we know it increased the droplet size. And so if we looked at a couple of different representative batches, you can see that the largest spans are often falling outside of the respirable range. And so if we narrow the span of that particle size distribution, more of the powder is going to be within the respirable range. And for us, because the inhaled oxytocin project is designed to actually get powder into the deep lung for systemic uptake, that's really important. That's a really desirable characteristic. And so improving the yield at the sacrifice of particle size is not something that we really wanted to do. Interestingly enough, when we looked at the moisture content and the glass transition temperature, we also saw that there was some sort of quadratic relationship going on here. We didn't do enough studies to really completely elucidate what was going on, but there was certainly a relationship happening. And we also saw that primarily that when you increase yield and production efficiency, you increase the moisture content, which decreases the glass transition temperature. And for us, the glass transition temperature is really important for stability. And so this really brings us to the point of the study, which is to find the optimal balance of parameters that can give high yields, but also not push the powder particle characteristics outside of our strict limits. And the next step was to use a response surface methodology to map all of that experimental space. And we used Design Expert software for this purpose. And so to summarize those interactions, what we saw was that improvements to yield and production efficiency weren't particularly difficult, but actually when you did do that, you often push the particle size outside of our desirable range, and that you should use the gas feed rate or the temperature to actually reduce that particle size back down. When we asked our model to actually provide some optimized processing parameters for a higher yield, what we saw was that actually we got a 12.5% increase in the raw yield and the production efficiency by 2.4 times, which was a fantastic result for us. And that was also while maintaining the D50 and narrowing the span as well. And so by elucidating a lot of the interactions between those processing parameters and our desirable particle characteristics, we were able to map the experimental space and improve the yield and production efficiency. And so by increasing liquid feed rate concentration, we could improve the yield, but actually we needed to use the gas feed rate and the glass transition temperature to actually balance the particle size back into the range. And so the data generated from this model was pretty robust and actually allowed the model to be as predictive as it was, which was fantastic. We saw some good improvements in yield while maintaining our powder particle characteristics. And the idea is that this study is going to act as a bridging study in between the R&D level and the commercial scale. And so by characterizing these relationships to the level that we did, it's actually going to allow us to address some affordability challenges at the commercial scale as well. And so thank you very much for listening to my DDL on-demand presentation. Thank you to the Inhaled Oxytocin team for helping me throughout my PhD. Specifically, thank you to Pete Lambert, Eddie French, and Jacob Harker. I definitely could have done this without you. Thank you to Michelle McIntosh and Tori Oliver for being my PhD supervisors. And don't forget, this research was supported by the McCall McBain Foundation, GSK, Johnson & Johnson, and the Australian government. Thank you very much for tuning in.